Revolution and Enlightenment. Then the second one is the famous inventor during Scientific Revolution and Enlightenment. Then last, we prepared some trivia for you.
What is Scientific Revolution and Enlightenment? According to Robert A. Hatch, University of Florida, scientific revolution is historical changes in thought and belief to changes in social and institutional organization that unfolded in Europe between roughly 1550 to 1700. It is the emergence of science in early modern period, when development in mathematics, physics, astronomy, biology, including human anatomy, and chemistry transformed societal views about nature. Some of them were revolution in their own fields. The scientific revolution began in Europe toward the end of Renaissance period and continued through the late 18th century, influencing the intellectual social movement known as the Enlightenment. What is Enlightenment? Also known as the Age of Reason. Intellectual and cultural movement in the 18th century. It emphasizes reason, over superstition, why it's been called Scientific Revolution and Enlightenment. Scientific Revolution because these changes in natural philosophy brought important transformation in what came to held as real. And Enlightenment, which enlightened everyone about the world through science over superstitious belief. Famous inventors during Scientific Revolution and Enlightenment.
Nicholas Copernicus from 1473 to 1543 was a Renaissance polymath responsible for what some have called the Copernican Revolution. One of the most important contributions of Copernicus was to the field of astronomy. Copernicus placed the sun at the center of the universe rather than the earth. The previous system, the Ptolemaic system, was geocentric, with the earth at the center of the universe. Galileo Galilei from 1564 to 1642 built on the foundations of Copernicus' work, also a firm believer in the heliocentric model. Galileo was placed under house arrest for much of his life for his belief after standing trial in Rome. He was called a heretic for believing that the sun, not the earth, was the motionless center of the universe. On 1609, Galileo improved his telescope. After hearing about Hans Janssen's latest invention, the telescope, Galileo decided to try to improve and apply it to astronomy. In the end, Galileo was able to improve it by 32 times.
On March 13, 1610, Galileo Galilei invented starry messenger. Galileo publishes a pamphlet involving his finding about space through his newly invented telescope. In his pamphlet, Galileo writes about his early discoveries about the Earth's imperfect moon, Jupiter's moons, and stars that aren't visible to the naked eye.
On March 5, 1616, the church bans the Galileo's writing. Eventually, the followers of the writings of Aristotle managed to convince the church that Galileo was going against the scriptures, which led to even more conflict with Galileo. The church then decided to completely ban Galileo's writing from the public and warns him not to hold or defend his doctrines. On 1623, Galileo wrote and published a book called The Assayer in Rome. It debates the difference between primary properties compared to other properties. In this book lies one of his most famous quotes of his lifetime. The Book of Nature is written with mathematical characters, which was the first look at nature at a mathematical way instead of the most common philosophical ways.
Isaac Newton, the most influential scientist of all time. On 1642 to 1727, took the current theories of astronomy a step further and formulated an accurate, comprehensive model of the workings of the universe, based of the law of universal gravitation. Newton explained his theories in the 1687 revolutionary work Philosophiae Naturalis Principia Mathematica, often called simply the Principia.
Tycho Brahe from 1546 to 1601. Tycho Brahe was a great astronomical observer and made accurate and long-term records of his observations, from which he derived his view of the structure of the solar system in which the moon and sun orbited the earth. While incorrect, his scheme was as viable by the knowledge of the time as was that of Nicolaus Copernicus.
Robert Boyle, from 1627 to 1691. A successful physicist at Oxford College. He worked with his colleague Robert Hooke to discern the properties of air, experimenting with air pressure and composition of the atmosphere. Boyle proved that the only part of air is used in respiration and combustion, and is thus credited with the discovery of oxygen. René Descartes, from 1596 to 1650, the inventor of deductive reasoning, one of the greatest minds of scientific revolution. He was a failure as a practical scientist, but a success as a mathematician, uniting numbers and from in his work geometry.
Johannes Kepler from 1571 to 1630. Johannes is responsible for creating Kepler's law of planetary motion. These laws include that the orbit of every planet is an ellipse, with the sun at one of the two foci, that a line joining a planet and the sun sweeps out equal areas during equal intervals of time, in that the square of the orbital period of a planet is directly proportional to the cube of a semi-major axis of its orbit. Kepler was one of the first to incorporate the field of physics in the field of astronomy. This caused some controversy. However, his ideas became more widely read and accepted after his death. Once Newton derived Kepler's law from a theory of universal gravitation, they become part of the theoretical canon of the scientific revolution. Giordano Bruno from 1548 to 1600, a renegade Italian monk. Bruno published 3 works: The Ash Wednesday Supper, on cause, principle, and unity, and on the infinite universe and its world, in which he laid out his philosophy that the universe was of infinite size, and that the earth, sun, and planets were all moving constantly within it, and were by no means located at its center. William Harvey, from 1578 to 1657. Through this section, Harvey was the first to demonstrate that the circulation of blood through the human body is continuous, rather than consisting of different types circulating through the veins and arteries, as had been previously assumed by the ancient Greek physician Galen. Claudius Galenos, from 129 to 199. An ancient Greek philosopher, physician, physiologist, and writer. Galen's work was the counterpiece of traditional biology and anatomy that had lasted through the Middle Ages. He exercised a dominant influence on medical theory and practice in Europe from the Middle Ages until the mid-17th century. His authority in the Byzantine world and the Muslim Middle East was similarly long-lived. In 162, the ambitious Galen moved to Rome. There he quickly rose in the medical profession owing to his public demonstrations of anatomy. His successes with rich and influential patients whom other doctors had pronounced incurable. His enormous learning and the rhetorical skills he displayed in public debates, Galen's wealthy background, social contacts, and a friendship with his old philosophy teacher Didymus further enhanced his reputation as a philosopher and physician. Galen's physiology was a mixture of ideas taken from the philosophers Plato and Aristotle, as well as from the physician Hippocrates, whom Galen reserved as the fount of all medical learning. Galen viewed the body as consisting of three connected systems: the brain, heart, and liver. Brain and nerves, which are responsible for sensation and thought. Heart and arteries are responsible for life-giving energy, and the liver and veins are responsible for nutrition and growth. John appeared from 1550 to 1617. In 1594, invented the mathematical tool of logarithms. He spent the next 20 years of his life developing his theory and computing an extensive table of logarithms to aid in calculation. 1614, he published description of the marvelous canon of logarithms, which contained the fruits of these labors. Santorio from 1561 to 1636 was one of the first to apply the evolving physical philosophy of the scientific revolution to animal biology. His experiments laid to the groundwork for the study of metabolism and the physical and chemical processes of the human body. Simon Stevin from 1548 to 1620 worked with geometry during the late 16th century, applying it to the physics of inclined planes and the hydrostatic surface tension of water. Additionally, he introduced the decimal system of representing fractions, an advance which greatly aids the task of calculation. John Wallis from 1616 to 1703, an English mathematician who contributed substantially to the origins of the calculus and was the most influential English mathematician before Isaac Newton. Wallis learned Latin, Greek, Hebrew, logic, and arithmetic during his early school years. He was ordained a priest in 1640 and shortly afterward exhibited his skills in mathematics by deciphering a number of cryptic messages from royalist partisans that had fallen into hands of parliamentarians. Wallis' appointment in 1649 as a Villian Professor of Geometry at the University of Oxford marked the beginning of intense mathematical activity that lasted almost uninterruptedly to his death. In his Arithmetica Infinitorum, or the Arithmetic of Infinitesimals of 1655, the result of his interest in Torricelli's work, Wallis extended Cavaliere's law of quadrature by devising a way to include negative and fractional exponents. Isaac Newton reported that his work on the binomial theorem and on the calculus arose from a true study of arithmetical infinitorum during the undergraduate years at Cambridge. The book promptly brought fame to Wallis, who has then recognized as one of the leading mathematics in England. In 1657, Wallis published the Mathesis Universalis, or the Universal Mathematics on algebra, arithmetic, and geometry, in which he further developed notation. He invented and introduced the symbol for infinity, the symbol found used in treating a series of squares of invisibles. Andreas Vesalius from 1514 to 1564. As a student and professor in Belgium and Paris, Vesalius was educated in the anatomical works and theories of the ancient Greek physician Galen, whose views on anatomy had long been started in Europe. Vesalius questions Galen's authority and published On the Fabric of the Human Body in 1543. It is considered the first great modern work of science in the foundation of modern biology. Francisco Salvius from 1614 to 1672. One of the earliest chemical biologists, he introduced the idea of chemical affinity to explain the human body's use of salt. He and his followers contributed greatly to the study of digestion and body fluids. Evangelista Torricelli from 1608 to 1647. Torricelli invented a barometer to measure air pressure. In 1643, this was a large step in the understanding of the properties of air, and the basic structure of the barometer remains the same today. A unit of pressure called a torr is named after him. Ed Marriott from 1620 to 1684. A botanist of the 17th century, Marriott sought to explain sap pressure in plants by describing a mechanism by which plants permit the entrance but not the exit of liquid. Claudius Ptolemus from 100 to 170 Common Era. An Egyptian astronomer, mathematician, and geographer of Greek descent who flourished in Alexandria during the 2nd century of the Common Era. In several fields, his writing represents the culminating achievement of Greco-Roman science, particularly his geocentric, earth-centered model of the universe, now known as the Ptolemaic system. Virtually nothing is known Ptolemy's life except what can be inferred from his writing. His first major astronomical work, the Almagest, was complete about 150 Common Era and contains report of astronomical observations that Ptolemy had made over the preceding quarter of a century. The book that is now generally known as the Almagest, from a hybrid of Arabic and Greek, the greatest, was called by Ptolemy the Mathematical Collection because he believed that its just a subject and motions of the heavenly bodies could be explained in mathematical terms. The opening chapters present empirical arguments for the basic cosmological framework within which Ptolemy worked. Otto von Guericke from 1602 to 1686. He invented air pump, did the first experiment with vacuums. The processes He demonstrated many of the properties of gases, such as then until disputed claim that they did, in fact, have weight. And Electrostatic, published on 1672. Francis Witt from 1540 to 1603, a mathematician who introduced the first systematic algebraic notation and contributed to the theory of equations. Witt's canon Mathematics sui ad triangula, or the mathematics laws applied to triangles, is probably the first Western European work dealing with the systematic development of methods utilizing all 6 trigonometric functions for computing plane and spherical triangles. Witt has been called the father of the modern algebraic notation, and in his introduction to the analytical arts in 1591, he closely resembles a modern elementary algebra text. His contribution to the theory of equations is the concerning the recognition and emendation of equations, in which he presented methods for solving equations of second, third, and fourth degree. He knew the connection between the positive roots of an equation, which in his time were taught as the only roots, and the coefficients of the different powers of the unknown quantity. Samuel Hartlib from 1600 to 1662, an English educator and agricultural reformer and a tireless advocate of universal education. Hartlib presented treatises supporting the views of the churchman reformer John Amos Comenius, such as a reformation of schools in 1642. He also translated many of Comenius' works, including Principe. After which Comenius visited England on 1641. During this time, Hartlib persuaded John Melton to write his pamphlet of education on 1644, which Melton dedicated to him. For his concern with the education legislation of the Long Parliament on 1640 to 1653 and his fight for the reformation of church and school, Hartlib was awarded by Oliver Cromwell an annual pension of £300, which ended with the Restoration on 1660. Marcello Malpai from 1628 to 1694, an Italian physician and biologist who, in developing experimental methods to study living things, founded the science of microscopic anatomy. After Malpai's researches, microscopic anatomy became a prerequisite for advances in the fields of physiology, embryology, and practical medicine. Marcello Malpai pursued his microscopic studies while teaching and practicing medicine. He identified the taste buds and regarded them as terminations of nerves, described the minute structure of the brain, optic nerve, and fat reservoirs, and in 1666 was the first to see the red blood cells and to attribute the color of blood to them. Again, his research and teaching aroused envy and controversy among his colleagues. Jean-Baptiste van Helmont from 1580 to 1644, a Flemish physician, philosopher, mystic, and chemist who recognized the existence of discrete gases and identified carbon dioxide. Van Helmont published a treatise on the water subspa on 1624 that criticized an earlier work and made him some enemies among physicians. Other tracts were issued on 1642 and 1644. At some time shortly before his death, Van Helmont gave to his surviving son, Francis Mercurius, the responsibility for publishing of all his work. The writings result was the Ortus Medicinae, or the Origin of Medicine, on 1648. What was the cause of the scientific revolution? Developments in Europe also helped bring about the scientific revolution. One development that helped lead to the scientific revolution was the growth of humanism during the Renaissance. The interest in the natural world carried forward into the scientific revolution. What started the scientific revolution? The scientific revolution began in astronomy. Although there had been earlier discussions of the possibility of Earth's motion, Polish astronomer Nicholas Copernicus was the first to propound a comprehensive heliocentric theory equal in scope and predictive capability to Ptolemy's geocentric system. Whose philosopher named that period scientific revolution. In the 20th century, Alexander Koyer introduced the term scientific revolution, centering his analysis on Galileo. The term was popularized by Butterfield in his Origins of Modern Science. Why was the scientific revolution is important? This is the significance of scientific revolution. This period saw the fundamental transformation in scientific ideas across mathematics, physics, astronomy, and biology in institutions supporting scientific investigation and the more widely held picture of the universe. The scientific revolution led to the establishment of several modern sciences. Scientific revolution and enlightenment similarities. The enlightenment and scientific revolution is similar because they happened around the same time. The scientific revolution is quite similar because it was when science flourished in the European world.
This is your presenter. I'm Anne-Lorraine Riales
I'm Maria Josefa M. Palau
from Best and Second Year Students saying,
We can do this para sa bayan at sa kinabukasan. For more updates,
don't forget to press the notification bell to get notified. So if you like this video,
please like and
ulit. If you like this video, please like and comment, then subscribe.
thank you for watching. See you next video.